Hello everyone, I am Santhosh Palanisamy and today we are going to see the topic about Hadoop Distributed File System. Okay, now we are going to see what is the main aim of this research paper. This paper describes the architecture of Hadoop Distributed File System, like exactly what's in the architecture, how it's going to perform, etc. The author K. Shvachko, who works at Yahoo, used this Hadoop system and he practically gave everything he experienced in this paper. Now, the overall goal is to show how Hadoop file system stores very large data sets and streams at a high speed to the users. It also explains how using distributed storage and computation across different servers helps us to grow in-demand data storage speed while making the cost economical. Okay, why do we need a Hadoop distributed file system? Why not a traditional file system? Okay, let's see. Solve the data scale problem. Traditional system couldn't handle the massive growth of data, leading to need for a new file system that could process the data reliably. So we thought of using Hadoop distributed file system and also prioritizing high throughput. If there's a huge amount of data, a single file system can't handle it quickly. So by using different servers and partitioning them, it helps us to make everything faster and also ensure fault tolerance and locality. Like in a large failure prone clusters, Hadoop uses data replication. Like we are going to make 3 copies of every data and it helps us to be safe even when there's a connection error in one of these computers. Okay, what is HDFS? Like, what is Hadoop Distributed File System? It was created by Doug Cutting and Mike Caffarella. Hadoop file system is a distributed file system designed for massive datasets and high bandwidth streaming. Like, it's used to handle large dataset at a higher speed. It is a core component of Hadoop, enabling the analysis and transformation of large dataset using MapReduce. Like MapReduce is an algorithm. It helps to split a huge data into small data and process it faster. The file system design allows computation capacity, storage capacity, and I/O bandwidth to scale by simply adding community servers. Like it added new system and new servers so we can handle it faster. HDFS sacrifices strict adherence to unique file system standards in favor of improved performance for the application it had. Like the file system is similar to the Unix one, but we are making some sacrifices so that our performance should be better. The core architecture separates file system metadata from application data. Like there's 2 types of data nodes in our system, and we are going to see about NameNode and DataNode. Okay, now this is the architecture of our Hadoop distributed file system. Our client is the user and he's going to give a request to a NameNode, which is like a master node, and the data nodes below that are the slave nodes for the master. Once the client gives a request, the NameNode receives the request, saw what the user needs to do, and he sends back which block he should access for his work. And the HDFS client gets the node he needs to access and he goes to the data node and he writes or read in the data node. That's how it's going to be work. Okay, now we are going to have an architecture overview. HDFS uses a classical master slave, as I said before. The name node is a master node and the data nodes are the slave nodes. And the name node has all the metadata, like which data are stored in which, all those things, while the data nodes has the actual data for all those. And HDFS client is just us using an interface to access it. And all the servers are fully connected using a TCP based protocols. Now we are going to see more about NameNode and metadata persistence. NameNode maintains the entire namespace as an image in RAM. It's basically what I said about how it has every metadata about the data nodes and their connections. It stores a persistent checkpoint and sequential modification log called the journal in local file system. Like checkpoint is basically save point at the previous one. What are the things we have at the previous checkpoint? And sequential modification log called journal is basically like if we made any changes in our system, what are the changes we made? We are just going to add the specific point. Okay, durability is critical. Checkpoint and journal can be stored in multiple storage directory because even if one node fails, we can access it using other checkpoint node and backup node. Checkpoint node periodically merges the journal and checkpoint. The backup node maintains as in memory synchronized copy of the name for faster recovery. Like checkpoint node has to merge both checkpoint and journals, so it's easier for us to access. And the backup node has every data from NameNode. So in case if NameNode fails, the backup node has all the metadatas. Now, DataNode operations and reliability. DataNode's reliability is achieved solely by replicating file blocks across multiple nodes, 3 copies, as I said before. Because we are using a distributed file system, in order to have fault tolerance, we are splitting the data into 3 copies so that even if one node fails, we can access it using another. Startup. Okay, what's a startup? A data node verifies the NameNode namespace ID and registers its unique persistent storage ID. So what happens is a name node and a data node need to verify each other to access a connection. So this is how it does. Heartbeats. Like every 3 seconds, a data node has to send a report to name node that the connection is alive. And block reports is more about a long-term connection. Every hour it needs to give a report on what it does for the past hour. Now let's move to client interaction and input-output flow. How the reading, writing happens in our system. The client first asks the name node for the block location, then reads the block contents directly from the closest data node. Like client asks for name node, then the name node returns the details to the client, then client moves to data node and he accesses it. Writing. The client is granted a lease for exclusive writing access. The name node nominates data nodes and client organizes them into a pipeline and writes data sequentially. So what happens here is the client gets the data block which we need to write from the name node, and we use that to form a sequential pipeline so that we write everything we need to in the data nodes. Down data locality. What data locality is used is to make the performance faster, we store related data next to each other. And durability check. Like clients verify a thing called checksum so that every data he has given is actually written in the data node, so nothing corrupted happened. Okay, key distribution block placement policy. There's a thing called block placement, how we are going to place each data in data nodes. The default policy optimizes for data reliability, availability, and aggregate read bandwidth. Rack aware policy. The name uses a cluster topology script to resolve the rack location of each data node. Okay, first replica places the node where the writer is located, places on 2 different nodes in a rack. This strategy ensures block replica are distributed across clusters, protecting against the rack failure. Now we are going to see how it does. Like you can see there are 2 racks. What happens is we are going to store data on one of the data nodes in the first rack 0, DN002 to DN02. What happens is the second copy of our data, we are going to place it on rack 1 instead of rack 0. So even if rack 0 fails, we have another copy in the rack 1 which we can access it. That's what basically happened here. The first replica is used on a rack, then second and third is used on a different rack. Okay, the thing is we are going to see how the replication management happen in the rack. The NameNode constantly monitors to ensure each block has independent number of replicas. The block under replication. The block is put in a replication priority queue. Blocks with only one replica receive the highest priority. Replication prioritizes placing the replica on a different rack if only one replica exists. Now over replication. The NameNode chooses a replica to remove. It prefers to remove a replica from the data node with least available disk space to balance utilization. So in under utilization, what happens is under replication, there is only one, there may be even 0 replicas in one rack. So it's better to put a replica from another rack and put it in this rack. And over replication, what happens is like there are more than one copies of the replica in the same rack. So we are removing that and we are putting it in another replica. Now we are going to see file input output details, reading and durability. When reading, the name node returns a list of block operation ordered by the distance from the reader. The client attempts to read from the replica first to maximize performance. A read attempt may fail, the target node is unavailable, or the replica is found to be corrupt when checksums are tested. The writer's release prevents other clients from writing but not from reading. HTML permit a client to read a file that is open for reading. So what happens here is we are telling how the reading happens. Okay, NameNode returns a list of block locations which we are going to read, and we are going to, instead of going to original one, we are going to use a closest replica, so it's faster. And also when we are accessing it, if the data node doesn't unavailable, then the file is corrupt. And also we can only one person can write and multiple persons can read. We can't have multiple persons writing in our data. Now we are going to see input-output optimization, writing pipeline in detail. The name node determines the data nodes that will host replicas, and these nodes form a pipeline that minimizes total network distance. The client pushes the next packet to the pipeline before receiving the acknowledgement for the previous one, limited by outstanding packet window size. HFresh operation, it immediately sends acknowledgement. So what happens is when the user gets the location for the data nodes, he immediately sends all his packets straight into the data nodes for writing, and he doesn't wait for acknowledgement whether that each packet is finished or not. So sometimes we don't know whether the packet has been correctly placed or not. HFresh is an operation where it tells us, oh, the packet is completed. So it's good for us to acknowledge it. And this is how it's going to happen. The client set up between 3 data nodes, and it gives us acknowledgement, and every time it sends a packet, we get a acknowledgement to the client, and at the end we are using a close so that our connection is finished. And these are some of the tools used by our HDFS balancer. This is a tool used to make the data between different nodes more balanced. Instead of one data node having every data, it balances out. Block scanner is used for verification that the stored checksums are good or not. And decommissioning, if the stored checksums doesn't match our checksums, then the data is corrupted. So decommissioning just removes those. Now we are going to see some of the applications of HDFS. Marketing and understanding customers, like whatever we like, whatever we post on the internet, it analyzes those data. HDFS stores this data, and it helps us to predict what we are going to buy next time. And also powering AI and machine learning. Since HDFS is basically used for high data transfer, using this in AI would help us make the model faster. Data archiving, like every piece of information in the old times, like there will be a different type of format, and it basically stores everything very good. Performance DFSIO benchmark. Now DFSIO benchmark is used to measure read, write, and append operations. This is only for the specific operation. We are not going to use the setup scheduling process. It's just for these 3 operations. And the benchmark for production cluster of at least 3,500 nodes without contention. That is, this is like an ideal situation. Like the reading operations can do 66 MB per second per node, and the writing operations can do 40 Mbps per second per node. But what happens is, this is an ideal situation, but in real life, in a busy one, there will be a lot of networking errors and a lot of clients using this. So average speed for reading is 1.02 MB per second per node, and for writing it's 1.09 MB per second per node. Now this is a comparison between 1 terabyte and 1 petabyte of data. Let's see, for 1 terabyte of data, so 1 petabyte of data, so 1 terabyte of data we have 1460 nodes, and 1 petabyte of data we have 3658. And you can see how many map and reduces function, which are basically like used for partitioning data and how the data is going to be. That is what map reduces, and we can see time taken for these. And also the time is more for petabyte because it has a huge number of data and it takes a longer time to process. And we are going to see how it's an aggregate for entire node in GBs and per node in MBs, how much time it takes. Like 1 terabyte takes 32 GB as an aggregate, and another petabyte it takes 34.2 GB. So it's basically similar. Per node is a little bit higher for terabyte because it has less number of nodes, but when you look at the average, because it has a lot of nodes, it has less speed. Now we are going to see performance NameNode throughput. The NameNode throughput benchmark is used to tell how much operation per second has been done by the NameNode. And this is the NameNode performance. Open file for read. It does 12600 operations per second. For creating file, the rate is 5600 operations per second. For DataNode heartbeat connection, each time it has to send a report, it does 300,000 operations per second, and for block report it does 639,700 block operations per second. The NameNode can process thousands of heartbeat per second without affecting other NameNode operations, so you can see how efficient it is. And my personal view and critique for this recovery, what are the strengths for this? Like, recovery is remarkably fast. That's one of the main reasons. Like, even if a system fails, it can reboot a system as soon as possible and recreate all those blocks in just 2 minutes. But the main weakness is NameNode, which has entire data in an image, metadata in an image, it stores all those data in RAM, and if there's less RAM, it's difficult for us to process it. And also, even when NameNode is broken down, we need to wait for it to recover. And my recommendation should be having a backup NameNode, so that even if the main NameNode fails, we can use that as a replacement. Okay, now we are going to see the research challenges. NameNode scalability. The NameNode RAM limits restrict the number of files and block addressable, and memory pressure causes unresponsiveness. As I said before, like, since NameNode stores everything in RAM, once the RAM is completely full, sometimes there will be unresponsiveness. So we need to change that. Many small files problem, like because we are dividing a large files into small files, sometimes it takes a lot of resources and it would be bad for us. And failover automation. The cluster is currently unavailable when the NameNode is down. So when the NameNode is down, we don't know what to do. So we need to have a backup node so that whenever it fails, we can have that. And data imbalance. Since I said before, NameNode just uses MapReduce to allocate everything. It doesn't always allocate everything balanced free. So balancer does an additional task which takes time to allocate everything in a balanced way. Now, conclusion and future work. Conclusion. HDFS successfully achieved its goal of providing a high durable, scalable, and high tolerance throughput file system foundation for batch processing on community hardware. So it basically does it work, but it still has some issues which we need to solve. The scalability. The team plans to allow multiple name nodes, which I said, to share physical storage using block pool identifiers, so that even if one fails, there's another there. And how it's going to do that? Automated failover. The new model has a thing called Zookeeper, which helps us to have two name nodes. So even if one fails, there's a thing called passive node passive name node, which takes place in the active name node. And long-term scalability. Future exploration includes truly distributed implementation of NameNode and storing only partial namespace in memory. So why do we need that? Because we don't need to store everything in the RAM, so that it takes all this memory in the RAM. Inter-cluster cooperation. Future efforts include providing greater cooperation between multiple clusters. So it's easy for us to share everything and it will be faster. And this is the reference paper I used for my presentation. Thank you. And if you have any questions, you can drop in our comments. Goodbye.